Welcome to this video. In this video we will study the mathematics of growth processes, and then in particular exponential growth, which is a term you've already heard about a lot. Now in mathematics we have functions that are particularly suitable for dealing with growth or decay processes, and those are exponential and logarithmic functions. So let's have a quick outlook of what we will see in the video. I will first point you to a video on the Euler number. Euler is one of the most famous mathematicians of all time, and there is a number, E, which is approximately 2.71, associated with his name. And this is particularly interesting when we talk about exponential growth. Exponential functions and logarithms are also very suited when we have phenomena that have scales that are very different in size. And sound and decibel is one of those examples, so I will tell you a little bit about that. After these introductions, I will give a definition of the exponential function, and we will show that the exponential function has an inverse, and the inverse we will call logarithm. So let's first see. Here is a link to a video of the British mathematician James Grime, and he introduces the Euler number. As he points out, I'm not going to repeat everything he says in the video because he does it much better than I could do, but E is a number that is not coming from geometry like for instance pi is. So pi comes from the unit circle, and we can introduce it in a geometrical way. Similarly, the square root of 2 is the length of a diagonal if we take a square with sides 1. Now E, which is 2.71, we introduce in a different way, and we will show that if we talk about exponential growth processes, that E is the number to deal with and that is very convenient to work with. So I urge you to watch this video. It's not very long. It's from a British channel on YouTube that makes videos on maths, and I will link to this video also in the description and in the PDF that you are watching right now. So one of the places where we also encounter the mathematics of exponentials and logarithms is when we describe sound. So we've already seen that sound is a periodic phenomenon, and it's a variation in air pressure. So my voice makes the air vibrate, those vibrations reach your eardrum, and your brain translates it back into sound, into words. Now your ear responds to pressure fluctuations that are as small as 10 to the power minus 9 times the atmospheric pressure, so the air pressure of air around us. The pain threshold, so the maximum pressure that your ear can reach without damaging, is 10 to the power 6 times greater. So there is a million in size difference here. And for these types of scales, logarithmic scale is very convenient. So decibel, which you probably know, is the unit of sound pressure, and sound pressure is defined as, well, you take the current air pressure divided by the atmospheric pressure of 1 bar, and then you take the logarithm multiply with 20. That's just for convenience that you get nice numbers to work with. So what does this number say? For instance, some typical sound levels, if we start from the bottom, if you hear leaves of a tree rustling in the wind, that's 10 decibels. And then it goes up. So bedroom at night is 30 decibels. Normal conservation, and this is 1 meter, is 60. Shouting 100 decibels, and the jet takeoff is 120 decibels. So if you would specify these sound levels in terms of the pressure, you would get very large or small numbers, and now you get nice numbers to work with. There are many other examples where you have similar scales, for instance the Richter scale that measures the impact of an earthquake, or the pH scale for acids, that also are logarithmic scales. And also if you have a camera, you know about aperture, the amount of light that reaches the sensor of your camera, and that is also a logarithmic scale. Now, to get there, first we need to recap a little bit on working with powers. So let A and B be positive numbers, and I will introduce a couple of rules that you'll already know, but just to recap, and I'll work with some examples to first introduce them. So if you have 2 to the power 2, that's 4 times 2 to the power 3. That's 4 times 8, that's 32, which is 2 to the power 5. So what you see, if I skip the intermediate steps, then you see that if you multiply 2 to the power 2 and 2 to the power 3, you get 2 to the power 2 plus 3. So the general rule here is that if you have a to the power p times a to the power q, that you can simply add p and q together. Another rule, if you have 2 times 5 to the power 3, that's 8 times 125, you can also do that. So you can either do that as 2 times 5 is 10 to the power 3, or you can say that's 8 times 125. They are the same. So you can bring the power to the individual factors inside the product here. So in general, with a's and b's, if you have ab in between brackets to the power p, that's a to the power p times b to the power p. There's going to be a list of these rules. So 1 over 2 to the power 3, that's the same as 1 over 8, which is the same as 2 to the power minus 3. So the general rule, 1 over 8 to the power n is a to the power minus n. The square root of 2 to the power 6, 2 to the power 6 is 64, square root of 64 is 8, and 8 is 2 to the power 3. So you see that you could do here 6 divided by 2. So the general rule is the square root of a to the power n is a to the power n over 2. 2 to the power 3 over 2 to the power 4, with what we have seen before, 2 to the power 4 is 1 over 2 to the power 4 is 2 to the power minus 4, and then we can add them together, and we have minus 1. So that's kind of combining what we have already seen. And the general rule is a to the power p over a to the power q is a to the power p minus q. The cubic root, the third root of 2 to the power 15 is 2 to the power 5, because if you do 2 to the power 5 times 2 to the power 5 times 2 to the power 5, you get 2 to the power 15. And the general rule is if you have the nth root, so here it says a 3, but if you have the nth root, that is the same. Oh, sorry, it's a p here, it's a bit small. That's the same as to the power 1 over p. So if you have a to the power q and then the pth root of that, that is a to the power q over p. So here we have q is 15, p equals 3, and then 15 divided by 3 is 5. Almost there, 2 more to go. If you have 2 to the power 2, that's 4 to the power 3, so that's 4 times 4 times 4. You get 2 to the power 6. So you can simply multiply 2 and 3 here. And the general rule is that if you have a to the power p and that whole thing to the power q, that is a to the power p times q. Then finally, if you have the square root of 2 times the square root of 3, you can simply multiply the arguments. 2 times 3 is 6. And in general, we have the square root of ab is square root a times square root b. So that's working with powers. Now let's look at the function y is 2 to the power x. So if you take for x 1, 2, 3, 4 and so on, and you plot those, then you will soon see that the graph looks like the red graph that is sketched here, and then 2 to the power 0 is defined as 1. Now if you would take 3 to the power x, you get the blue curve, and you see because 3 is larger than 2, it's steeper. So for small x values it already increases more, and I have emphasized that by also plotting 4 to the power x. So this is what those graphs look like. So what we can see in general, some properties. we call a constant time b to the power x, where b is some positive number. We call that an exponential function, and this number b is called the base. So what you see is that this thing has base 2, this thing has base 3, and the last one has base 4. And general properties for functions with b bigger than 1 is that if x goes to minus infinity, so if we look here, we let x go to minus infinity, you see that all of them go to 0, so y equals 0 for x going to minus infinity. You also see that for x equals 0, they all go through 1. They all go through to infinity for x going to infinity. The function is always positive. And what you also see, that's increasing. So these 5 properties are general properties that any function f(x) is b to the power x with b bigger than 1 has. So you may wonder what happens if I take my base, if I take it less than 1. For instance, a half to the power x. Well, you can easily find out what they are, because if I take that example, so a half to the power x, I can rewrite that with the rules we have seen for powers as 2 to the power minus x. So we have already seen what 2 to the power x looks like. And then if you replace x by minus x, it means that you're flipping in the vertical axis. So you just mirror the function in the y-axis, and then you have the graph. So here I've done that. These are the graph that we have already seen on the previous slide. And if you now mirror them in the vertical axis, so here is the vertical axis, and you simply flip them around, then you have the graphs of these functions. So they are related. So this is b bigger than 1, and this is b smaller than 1, the base. Now, what I would like to do next is look at the slope of the tangent line of the function b to the power x with b bigger than 1. So we're going to look at this situation, and I'm going to draw, if you look at the black curve for instance, I'm going to draw the tangent line here at the origin. So what we then have is, there is a little animation here, so let's start the animation. Like this. So what you see happening here is that I plot f(x) is b to the power x, and I take different b values. So for a different b value you get a different graph. And what you can see is the dashed line here is the tangent line, and this m that you see here is the tangent, the slope of the tangent line. And if I am going to, let's see, I want to pause this, and I am going to put it such that m is close to 1. So here m equals 0.99, and you see that b equals 2.7. Now, if you want to choose the b such that the slope of the tangent line equals 1, then we find the number e. And if you would compute that, you would find that e is approximately 2.718. So this is called Euler's number because he came up with this definition. Now, there is a theorem that e is the limit of n going to infinity 1 plus 1 over n to the power n. That is a bit of a strange limit, and you'll have to believe me here, I'm not going to prove it. If you watch the video, the initial video, then this makes sense, because then you can interpret this as an interest rate. So I recommend that you indeed do watch the initial video here. Now, another interesting thing that combines some of the stuff that we have been studying before is we now have this, this function this exponential function. And what we have seen is that in general, so b to the power x, so for b equals e, the Euler number, but basically for any b that's bigger than 1, but also for b less than 1, we have seen that the function is either increasing or decreasing, which means that it is 1 to 1. If I intersect it with a horizontal line, it only crosses the graph once, not multiple times. So it either doesn't cross it, for instance, if I pick negative values, and otherwise only 1. So it's 1 to 1, which means it has an inverse. And that inverse is special, and that inverse we call the logarithm. So what we have, if x is b to the power y, then y is the b log of x. So this is definition of logarithm. For instance, say x is 10 to the power 3, so 1000. Then apparently b equals 10, that's the base, and y equals 3. So what we find on the left here is that 3 is the 10 log of 10 to the power 3, which is the 10 log of 1000. So the 10 log of a million is 10 to the power 6, is going to be 6, and so on. So this is how that works. They're each other's inverses, and here you see the definition. Now, we know that b to the power y is always positive, so that means that you can only define the logarithm for positive x values. Some common choices, so logarithms that you often see are b equals 2, b equals e, so the Euler number, and then we write ln x, the natural logarithm, and that's the one we will work with most. And also you see b equals 10, and often in technical literature people simply drop the 10 here and they simply write logarithm of x, and then very often they mean the 10 log, but it's a bit unclear because sometimes in textbooks also used for the natural logarithm. But we will be very strict. So whenever we write something, we either write which logarithm we have, so we add the base to it, or we write ln x, and ln x is the natural logarithm. So we have that ln x is log with base e x. Then finally, depending on the textbook, and also Canvas uses a bit of a different notation, so that the base is written to the left of the logarithm and as a superscript, and our textbook uses a subscript. So the most commonly used functions in respect to exponential function logarithms are e to the power x, so we choose b equal e, and as it's already stated, it's approximately 2.718, and that just continues. And then ln and e to the power x are each other's inverses, so this relation holds for all x. Any real number you can pick, this holds, because you can always compute e to the power x that is going to be a positive number, and then you can take the ln. The other way around also, but then you have to take the ln of x, and ln x is only defined for positive x, so this one only holds for x positive, otherwise you cannot write down ln x. And we will give you some questions with logarithms, and one of the things that you could have is the following example to solve equations with logarithms. So example, solve ln x plus 5 equals 3. So now you would like to know for which x value does this hold true? And what you should do here is use that ln and e to the power x are each other's inverses. So I'm going to say, well, e to the power ln x plus 5 should apparently equal e to the power 3. So this is just a constant, right? So e is something like 2.7. You can just punch this into a calculator and you will get a result. This is just a number, a constant. On the left side, e to the power ln, they cancel. So we find that x plus 5 equals e to the power 3. And you see that x itself is apparently e to the power 3 minus 5. And we are done now, but just as a check, let me plug the value that we found into the expression here. So I'm going to compute the ln of x plus 5. So that's the ln of e to the power 3 minus 5 plus 5, which is the ln of e to the power 3, which is indeed 3. So indeed we have found the correct solution here. Now let us look at the graph of the logarithm. So the ln we've already seen, we could find that by mirroring the exponential function. It's the inverse of e to the power x. We know the graph of e to the power x. If you mirror in y equals x, then you get this graph. If you make the base larger, so this one is log e of x, and e is approximately 2.718. So you see that if you make the base larger, you go to 10 from 2.7, then it's a bit flatter. It goes to infinity slower. If you look at the log 2, so now you decrease the base, you see that it goes to infinity faster because the black curve is above the red curve. In general, what you see is that we have the following properties. If you let x go to 0 from above, then there is a vertical asymptote, so the function goes to minus infinity. It is not defined for x equals 0. It crosses the horizontal axis at 1, so if you take the logarithm of 1, you find 0. You see that it goes to infinity, but it goes to infinity incredibly slow. And you can see that if you take the 10 log of 10 to the power 6 of a million, it's 6. And if you take the 10 log of 10 to the power 20, which is an incredibly large number, you get 22. So it does go to infinity, but very, very slowly. And you see that the function is increasing. So this is for base bigger than 1. So 2, e, 10. If you take b less than 1, then you can rewrite it. So I've done that here. So what you do is you say x is b to the power y. That is the same as 1 over b to the power minus y. So what you see is that minus y is log 1 over bx. So what we have found is that the logarithm of 1 over b is related to the logarithm of b, but it gets a minus sign. And what that means is that if you have here those logarithms that we have seen before, if you put them upside down, so here I have 2, here I have 1/2, here I have 10, here I have 1 over 10, that means flipping the graph in the horizontal axis. So then you know what the graph looks like for b less than 1. Now, you may wonder, why are logarithms useful, special, or why do people use them? And the reason for that is that they can make big computations that are hard to do by hand. They can make them a lot easier, because what they can do is multiplying two large numbers, they can turn that into an addition. And let me try to make that clear to you. So you know that if you take 10 to the power 3, 1,000, and you multiply that with 100,000, then you get 10 to the power 8. So what you see here is that 8 is 3 plus 5. If we use logarithms, then the 10 log here gives 3, 5, and 8. So written differently, what we have is that the 10 log of 10 to the power 3 times 10 to the power 5 is the sum of the logarithms of the individual factors. So what you can do is, if you have two positive numbers, you could compute that 10 logarithms and call them u and v. Maybe you can look them up in a table. And then if you're interested in the value of x times y, instead of multiplying x and y, you can simply add u and v together. And then x times y is 10 to the power u plus v. So using logarithms, you can turn multiplication, like we have here, into addition, adding u and v together. And I have tried to make that even a little bit more clear. So the idea is that if you have two numbers, x and y, positive numbers, and if you have some way of easily finding their logarithm, and one way that people used in the past before calculators is use a slide rule. So with a slide rule you could easily find the logarithms. So then you can find u and v, you can add them together, and then if you do the inverse, so here is a red arrow computing the logarithm, here is a black arrow doing 10 to the power z, then you can find x times y. So if you have two big positive numbers x and y, and you would like to find x times y, instead of doing this route, so we don't do the multiplication, but we do logarithms, add u and v together, and then go back, and then we can also find the product. And that is why, one of the reasons, logarithms have been defined, introduced into mathematics, and how they are being used. A few properties. So we've already seen that if you take the logarithm of x times y, it is log x plus log y. As a consequence of that, you see that, so let me write that here. If I would now do the log b of x times x times x and so on. So let's say that this is the log b of x to the power n. Then I can write that as log b x plus log b x plus and so on plus log b x. And then I have, if I have n factors here, then I get n terms here. So then I have that this equals n times log b x. So what you see, what you can do apparently, is if you have to the power n inside the logarithm, you can write it in front of the logarithm. So an exponent in the argument, you can put it in front of the logarithm. And that is the second line here. So if you have the log b of x to the power y, you can write it as y times the logarithm of x. And then the last one. So here you can derive that as log b x over y is log b x times y to the power minus 1. Then I split it using the first property. And then I can write the exponent in front of the logarithm. So I find log b x minus log b y. So that's the derivation of the last rule that we have here. So of course you don't have to learn these rules by heart, but you should be able to work with them. So let us look at an example how you can use that. So example. So one of the questions that we might give you is to rewrite the natural logarithm x to the power 3, y to the power 4 over z to the power 5. And you can write this in terms of the ln x, ln y, and ln z. And the way you can do that is just use the rules. So first we have a quotient. So I can write this as the ln of the numerator, x to the power 3, y to the power 4, minus the ln of the denominator, z to the power 5. That's the third rule from the previous slide. If I go back here, then I've simply used what it says here. Now, the first one is x to the power 3 times y to the power 4. So I can write that as the ln x to the power 3 plus the ln y to the power 4 minus the ln z to the power 5. And then finally I can put the exponents in front of the logarithms. So I find 3 ln x plus 4 ln y minus 5 ln z. So that is how you can use these rules, how you can play with them, how they work, and why they may be useful. So here is those properties of the logarithm again. And here is an important corollary. Any exponential function can be written as an exponential function with base e. What that basically tells us is that we only need to be able to work with e to the power x, and any other 10 to the power x, 4 to the power x, or whatever to the power x, we can always rewrite that. And that is being done here, but let's look at that together. So if you have y is b to the power x and b is some constant, then what you can do is that you take the ln on both sides of the equation. Then you use it, you can write the exponent in front of the logarithm. So this is the same as x times ln b. So the conclusion now is if I now take e to the power ln y, that's the same as e to the power x times ln b. E to the power ln y, e and ln are each other's inverses, so I find that y equals e to the power x ln b. So apparently a general function b to the power x with these intermediate steps, you can write it as an exponential function with e as a base, and this is how you can derive that. And to tell you the truth, I don't know this formula by heart, so the formula that is listed here, but its derivation is quite simple, so I can always do this derivation, and that's easy to recall. If we have something like this for exponentials, we probably also have that for logarithms. So indeed, any logarithm with base b can also be written in terms of ln's, and the way that goes, so let's also do the derivation together. So we have, say, y is the b log of x. That means that x is b to the power y. That's the definition of the logarithm. Now I'm going to take the ln. So I find that ln x is ln b to the power y is y times ln b. That's one of the properties of the logarithm. So I find that y equals ln x divided by ln b. So again, if I have the b log of x, I can also write that in terms of natural logarithms like this. And the reason we do that is that e to the power x and the natural logarithm of x, they are nice functions to work with. And we will see why that holds true in a future video. But this is how you can rewrite them. And as I said, I don't know these formulas by heart, but I do know their derivation. So that's what I normally use. So how could you possibly use this? For instance, and that's the final example for this video, if you have y is the logarithm with base 7 of 12. So this is some number, but say that your calculator, if you're using a calculator, doesn't have the 7 log, the log with base 7. So what you can do, what this means, is that 7 to the power y equals 12. That's just rewriting what it says. Now we can take the ln. So we have that ln 7 to the power y equals the ln of 12. So y times ln of 7 equals ln of 12. And we find that y is the same as ln 12 over ln 7. So if you have a calculator that only has the natural logarithm as a logarithmic function, you can compute any logarithm by using this trick or rewriting or whatever you want to call it. So that brings us to the end of this video. What have we seen? We have seen how you can introduce the Euler number. I have given you the link to the video by James Grime for that. How we can work with power, some of the rules. How we can define the exponential function, the logarithm as the inverse, and then how we can write any exponential as e to the power something, and how we can write any logarithm in terms of natural logarithms, ln, the logarithm with base e. That wraps it up for this video, and I hope to see you in the next one.